These are notes on phase change and the energy involved in phase change. So we're looking at when we have a phase change, how the intermolecular forces have to be either broken or formed depending on what the phase change is. And just a reminder, remember IMFs? So we're talking about LDFs, dipole-dipole, and hydrogen bonds. So you guys, you watched the video with Tyler DeWitt, and this is just kind of showing you those IMFs. So ice, remember, it kind of forms that hexagon shape. The IMFs have to be broken in order for you to be able to form liquid water. And the IMFs of the liquid water have to be broken in order to form water vapor or gas. So remember, the IMFs it takes energy, so energy is going into, it's an endothermic process when I go this direction, and then energy is coming out of the gas for it to condense and form a liquid. So that's an exothermic process, and then forming ice is also exothermic. So what happens to something when we have a phase change? What happens to the temperature? We know that water boils at 100 degrees Celsius at normal atmospheric pressure, and we know that water melts at 0 degrees Celsius. This is a I'm gonna push play in a second. What this is going to show you is an animation of the temperature, which is on the y-axis, and time on the x-axis. This would be if we were continually heating a piece of solid ice, and then we melt it, and then we have the liquid, we heat the liquid up, and then we boil it, and then we have the gas. So I'll show you. So this is the solid. And then once you get to the melting point, notice that the temperature doesn't change. And then when it's all liquid, again, the temperature's going up. Until you get to the boiling point. And then at that point, the temperature stops changing. So it seems strange that as you're heating something and you're melting it, it's going to just stay at 0 degrees Celsius. And when you're boiling something, no matter how long you boil it, as long as there's some water there, it's going to boil at 100 degrees Celsius. So here's another picture of what we were just being shown, and it's just showing you, you know, that going from the solid, once it's at the melting point, the temperature isn't changing. And why is that? You know, this is because all of the heat energy, so this would be like if we were continually heating something like with the sun or with a burner, hot plate, all of the heat is being used to overcome those attractive forces between the molecules of the solid, or to break those IMFs. And then it's stored in the liquid. So while this is happening, the temperature doesn't increase, but the energy is changing, and the potential energy of the gas, for example, is much higher than the potential energy of the liquid. So here's another picture kind of, you know, just showing you the phase changes. We already talked about the fact of them being endothermic going this way, exothermic going the other. But think about now in terms of stored potential energy. Ice has the least amount of stored potential energy, and steam, water vapor, has the most potential energy. So we're going to talk now about molar enthalpy of vaporization. This is the amount of heat to vaporize 1 mole of a liquid at its boiling point. There's also molar heat or enthalpy of condensation, which is the opposite but an equal value. And there's also molar enthalpy of fusion, and I will talk about that in just a second. So we're going to be starting to see the letter H, which is enthalpy. So this, like positive delta H or delta enthalpy, means that the energy is going into the system. So it would be an endothermic process. And when the enthalpy, the change in enthalpy is negative, then the energy is coming out of the system, and it's an exothermic process. So this is your packet. I think this is page 3 of the packet that we have that you hopefully have printed or you have opened. So this is just showing you that for different substances, like let's say we have acetone, it's going to boil at 56.2 degrees Celsius. That's nice, and we're going to use those values later. What we're really looking at today, though, is the molar heat of vaporization. Notice these are all positive, and they are for vaporization. But if I'm going to change 1 mole of acetone from a liquid to a gas, it's going to take 32.1 kilojoules to do that. I can go the opposite too. So I could also change this vaporization and say molar heat of condensation. In that case, for the acetone, for every 1 mole of acetone that goes from a gas to a liquid or it undergoes condensation, it's going to release, so it'd be a negative 32.1 kilojoules for every 1 mole. So we're going to focus on the molar heat of vaporization column and then also the molar heat of melting. So these are positive again. So when I melt something going from a solid to a liquid, it's going to be positive endothermic. But the reverse, if I go from a liquid to a solid, we call that the molar heat of fusion or the molar heat of freezing. So in order to look at water, we know that at 0 degrees it can melt and freeze. So if I'm going to melt 1 mole of water, it's going to take 6.00 kilojoules to get that all to melt and go from solid to liquid. And if I take the liquid and freeze it, this would become a negative 6.0, and it would have a molar heat of fusion of negative 6 kilojoules. So now that we know how to read the molar heat or enthalpy change of those different phase changes, we can calculate exactly how much energy, potential energy, is either lost, given off, or absorbed, taken in, by taking the enthalpy of the phase change and multiplying it by the number of moles. So here's an example. We have 3 moles of ethanol. So when I do these problems, I'm going to use dimensional analysis. So 3 moles of ethanol, which is C2H5OH, and I know that from here. So dimensional analysis, so I'm going to just place that over 1. And then the question is asking the energy needed to melt. So I'm interested in this column. Oops, not the melting point, sorry, over here, the actual. So it's going to require 8.30 kilojoules to melt 1 mole of ethanol. So my moles cancel, and I end up with 20, 34.9 kilojoules. So that would be how much energy to melt 3 moles of solid ethanol. So another problem here is the little twist here is that we're not in moles, so we can still use dimensional analysis to go from gram to mole, and then the energy is going to be released this time. So I will show you how to do this. So 15 grams of water, and so we're talking about water, and I'm in the way always. Over here, and we're going to condense it. So we're interested in the heat of the molar heat of vaporization or condensation. Before I can use that value though, which is in kilojoules per mole, I need to get to moles. So I know that water has a molar mass of 18.02, and then now I'm ready to use the 40.7 kilojoules per mole. And that amount of energy is going to be released. You can put a negative there, you can put a negative in the answer, but also just the fact that we say release implies. So I would be okay if the question's asking just how much energy is involved, then you would want to for sure make it a negative at the end. So when I do this, I get negative 33.9 kilojoules. So when 15 grams of water goes from a gas to a liquid, it'll release 33.9 kilojoules. I hope that helps.